Okay, so here they're asking us which graph represents an exponential equation. So we're just identifying the different types of functions we're given. So we're not going to get too much into how to derive the formulas for each of these images. I wanted to initially, but I would just be rambling on for a long time because there's a lot of fun mathematics behind this. But we'll come back to that in other videos. We'll get to the fun mathematics on how to find the equation for all these lines and some of the logic behind that. Here we're focusing more on general characteristics and shape of each function. This first one right here, what kind of a function is that? Well, it's a linear function. And you could tell this is linear because what the shape is a line. In other words, it's a constant rate of change. So if I go up by 2 here, I'm going to go over by 4. Okay, that's my rate of change, and that always works, right? I can go back 4 and down 2, or any other scaled up or scaled down model. Instead of going up by 2, change in y is 2, and then over x 4, we can go up 1, right? Up 1 and over 2, which equals going up 2 and over 4. 1 over 2 is equal to 2 over 4. No matter how we look at this, the rate of change, not the line itself, but the rate of change is proportional. That's a linear function. This function right here, you get used to it. The functions that look like this type of V shape right here are different variations of the absolute value function. Basically, a typical absolute value function might look a little bit like this, where it's centered on the origin, right? So what this is saying is, let's say x is equal to 1. Well, then y is equal to 1, right? So your point is right here on the line. If x is equal to -1, well, you imagine you would be taking the absolute value of x, right? This is the graph of the absolute value. What's the absolute value of -1? Well, if I plug in -1, the absolute value is still +1. If I plug in 2, I get 2 for absolute value. If I plug in -2, I get +2. So you see there's this kind of symmetry here. It's almost like taking two linear equations, right, and having them meet at some central point, in this case the origin. Now this absolute value function here, it's been shifted over to the right, and then down. So the function, I think the equation would be something like f of x equals, and I'll let you play with this one, x plus 2 minus 2, like that. But it's fun to talk about this, but again, I'll be talking for a while. Oh, and sorry, by the way, in the first one, it crosses the origin, so our y-intercept is 0, and our slope is 1 over 2, so it's 1/2 x, and that equals y. In this one, we have a parabola, and a parabola is this type of quadratic shape where we can draw a line of symmetry through the vertex, which is the point, either lowest or highest, or most left or most right point, and then fold your function along the line of symmetry. In this case, it's a parabolic, right, or quadratic function. It's not exponential. Even though the quadratic formula uses the idea of x squared, that's not what we're talking about. When you're talking about an exponential function, choice 4 here, and that is, it's some number, let's say a, different color, right, and the power is actually the variable, right? So the variable is in the exponent, and that's what an exponential function will look like. In this case, I end up deriving the formula. It's something nasty looking, like square root of 2, I believe, times 1 times square root of 2. I think it was this, 2 times the square root of 2 to the x power, and then minus 8 equals f of x. Something like that, if I'm getting it right. But that was just one way to do it here. But without getting into the fun mathematics and how to derive that formula, I'm just pointing out, I want to talk about visually what does an exponential function look like when you have the variable and the as the exponent. Well, what you're going to see, and typically you wouldn't see it like this, and that's all we're doing here is focusing on visuals. If you had a graph, say this is your y-axis and this is your x-axis, typically what you'll see for an exponential function is something like this, growing, oops, start over. At first it's very close to the y-axis. It grows ever so slowly, and all of a sudden it starts to shoot up, right, and grow at this crazy rate. This is what exponential functions typically look like. What you'll see is this really slow growth. or a chunk of the graph where the rate of change is slowing. For us, in our graph, it's right over here. And again, that just means the rate of change is slowing. Well, it's almost flattening out, right? In other words, the y values aren't changing much anymore, even though our x values are changing dramatically. So it's like the rate of change is slowing, the slope is slowing. And then at some other part, you'll see this just incredible growth, right, happening. So those are two quick ways to identify this exponential function. Notice in the parabola that the rate of growth does slow as you get over here, and in fact along this line is 0. But then it goes back and increases again. The exponential function, as it goes right infinitely here to the left, in both cases, it could be reversed, but in this case to the left, what's going to happen, you can almost imagine it, right? As this exponential function keeps going, it's going to get ever so close to 0, but never actually cross it or touch it, right? It's going to kind of hover there, almost infinitely close. And that's this idea of it, where it hovers really, really close to some line. It could be 0. In our case, the line's down here at 1, 2, 3, 4, 5, 6, 7, 8, right? So here are lines at y, y equals -8. So this exponential function is hovering down here and never going to touch this line. And here are lines at 0, but that idea is the idea of an asymptote, right? Asymptote. That's just saying, hey, the exponential function will approach some line, in this case over here, but never actually hit it. In the other direction, the line, it's just the rate of growth is dramatically increasing, but eventually, right, it works its way along to the right. Here, though, what's so interesting with the exponential function is that there's a gap here that'll never be closed, even though it becomes amazingly small. So that's what we can look for in the exponential functions. And again, parabolic look like a U shape or a parabola. The V shape is like an absolute value, and a straight line is linear. So just identifying the functions. We'll have fun in other videos really talking about some of the beautiful mathematics behind this stuff. Thanks.